Yeah. What? Okay.
Hey team, how's it going? Sorry I'm a minute late, but go ahead and get started whenever you're ready.
Okay, hello everyone. Hello everyone, this is radar-based motion and recognition, classification of drones and birds using convolutional neural networks applied to radar micro-Doppler spectrogram images. I'm Solomon, we have Mohammed and Taru, and our advisor, Dr. Zhang, and our coordinator is Dr. Thompson. Next slide, please. So our problem statement includes interfering with aviation. The risk of drones technology interfering with navigational tools are high and crashing into a plane and causing serious damages, as the image on the left shows. And also, such as the sporting events, an athlete was competing in a triathlon, and a photographer's drone crashed into them or drilled into that person as they were competing. The image on the right shows. We also have other issues such as wildlife. The U.S. National Park has already banned drones due to an unpleasant incident involving a careless drone pilot startling a herd of endangered bighorn sheep, and also smuggling drugs or conducting other illegal activities. Next slide, please. So our proposed solution for our problem statement would be using the radar micro-Doppler effect to detect drones and birds, and using a machine learning algorithm that uses the extracted information to accurately identify whether we have a drone or a bird. So this image here on the screen shows how we first get the image, detect the image using the radar. And after that, we take the image and we process that image. And from that processed image gives us an image that we can use for our classification. We'll feed it to the AI. And the more data it has, the more accurate we can be with determining if it's a bird or a drone. Next slide, please. So these are some of our functional requirements that we had to do. So for our distance was about 19.78 meters with the target value. For a pass or fail, we wanted a 90% chance of or greater of a pass or fail for detection of distinguish between the two. And for the signal, if we had more than one bird or drone, for us, it had to be more than 1.5 meters apart. Next slide, please. And one of our design constraints for our budget was which was $107.50. And then for our distance it couldn't be no greater than 120 meters because of the FAA regulations. And also for the Doppler that we were able to obtain, we were limited with our equipment of 5.8 gigahertz for the gigahertz. Next slide, please. So this is a picture of the radar that we use to conduct the experimentation. As you see, we have two antennas, one for the transmitter, one for the receiver. And we would take that signal and then we would modulate it. And then from that, after modulating it, we will process the module. And as you can see, this radar has the 5.8 from 5.6 to 6.0 gigahertz, which is what we had to do for our limitations. Next slide, please. And this is the software after we used to connect the image that connected to the radar. So right here is the control panel on the left-hand side, and the control panel, it includes selecting the waveform and the operating parameters and filtering types and recording the data. And then the graphical panel includes selecting the graphical representation of a signal in time and frequency domain. Next slide, please. And this for experimentation, we had some challenges as far as just having access to a real bird to conducting experimentation. So our solution to fix that was an RC bird. So we just use that while we conducted our experimentation. Next slide.
These are some of the major concepts used in our project. I will talk a little bit about the Doppler effect and the short time Fourier transform, and then I will present simulation and experimentation results. Christian Doppler is known for his discovery of the famous Doppler effect. He discovered that the frequency of an observed wave depends on the relative speed of the source and the observer. In this equation, F sub D is the Doppler frequency, F is the Doppler's carrier frequency, and F is the radar's carrier frequency, and V is the radial velocity of the object. When the object is moving away from the observer, we get a negative Doppler shift, which is proportional to the relative speed of the object. Next. For the micro-Doppler effect, we can identify different objects through their distinctive micro-Doppler signatures. Any object that produces any sort of micro-motion, in addition to its general translational motion, can give a unique signature, which we can use to identify it. We can obtain these signatures by analyzing frequency components of the signal in the joint time and Doppler frequency domain. Some examples of objects that can be identified using this tool are a helicopter or a drone with rotating rotors, a bird with flapping wings, and a car with running an engine. The modulation of the return signal contains harmonic frequencies determined by the carrier frequency, the vibration rate, and the angle between the direction of vibration and the direction of the incident wave. For analyzing time varying frequency features, The Fourier transform is not suitable because they cannot provide time-dependent frequency information. There are several methods that we can use to obtain time frequency information, but for this project, we use the short-time Fourier transform. And this method performs the standard Fourier transform on short time windows rather than taking the Fourier transform of the entire signal. The output is a spectrogram which gives both frequency and time information. Next slide. We use this mathematical model which represents the time domain signature of rotor blades. And in this figure, the radar is located at the origin and the rotor blades are centered at the origin of the body of the drone or the helicopter in this case. The rotors here are rotating about the z-axis in a uniform manner. The top equation is the mathematical model we use to simulate the movement of a drone's rotor, where capital omega is the rotational speed of the rotor, L is the length of the blade, phi is the phase function of the scatterer, n is the number of blades, and phi naught is the initial rotational angle. We use this model to simulate the radar returns of the rotation of the blade as a function of time, and then we perform time frequency analysis to obtain spectrogram, which will be used to identify the object based on the unique signature it produces. Next slide. The micro-Doppler signature of the rotating blade rotor is shown here. This is a three-dimensional plot that shows frequency versus time on the y and x-axis and magnitude on the color axis. The redder the color, the stronger the signal. These results are from a summation of range profiles within a range gate where the blades are located. The joint time frequency transform used to generate the signature is the short time Fourier transform. And from the spectrogram shown here, we can see a periodical signature, which is a unique signature to the rotation of a rotor mounted on a drone. On the left, we have a rotor with 3 blades, and on the right, it has 2 blades. The time it takes for one blade to complete one cycle is, as you can see, T sub C, and it can be used to estimate the rotational speed of the rotor. Similarly, we can obtain the length of the blade given the rotational speed. We can simulate different images by varying some initial parameters, such as the rotational speed, the number of blades, the number of rotors, and the length of the blades, as well as the translational velocity of the drone. By varying these parameters, we can obtain different spectrograms, which can be used to train a classification algorithm that can accurately identify a drone. Next. A bird wing is shown here, where the wing is defined by the wingspan, chord, upper arm, forearm, and the hand. Wing flapping is the elevation and depression of the upper arm or forearm around joints with certain flapping angles. Wing twisting is a rotation of the wing about its principal axis, which results in the elevation of the trailing edge and depression of the leading edge. Sweeping is the forward protraction or backward retraction of the shoulder. Flapping, twisting, and sweeping consist of the basic bird locomotion. We use the model proposed by Wong to simulate the movement of a bird in MATLAB. I will now show a brief animation of the bird simulation. This is the micro-Doppler signature we obtained by using the bird's model. Similar to the rotor, we can estimate how fast the bird is flapping its wings. On the left, the bird is flapping at a frequency of 1 Hertz, which is just the magnitude of the wave. This is the correct parameter we used in the simulation, so it checks out. Similar to the blade, we can simulate many spectrograms by varying the initial parameters, such as the flapping frequency, how fast the bird is flapping its wings, the length of the wingtip, and the translational velocity, how fast the bird is flying, as well as the flapping angle. Next slide. For our experimentation, we use the fan to simulate the motion of a blade, which is much similar to a rotor mounted on a drone. The fan's rotor spins much slower and has a longer blade length, but nonetheless, the two are very similar. Here we have the micro-Doppler signature of a fan's blade, and the stronger the signal shown on the bottom left comes from the motor poles. This makes sense because the poles are made out of metal coils, which should give a stronger reflection due to the higher radar cross-section. On the right, we have the radar signal, which is clearly periodical and reflects the movement of the rotor. And the time between two peaks is the time it takes for the rotor to complete one full cycle. Next one. In this experiment, we started the fan and then quickly turned it off so that the rotor would exponentially slow down, and then started recording the data at the same time. On the left, we see the Doppler frequency decreasing as the fan's rotor slows down. And at t = 7 seconds, we can see the Doppler is almost 0, which confirms our experiment and signal analysis results. For the birds experiment, we use an RC bird, and because we could not use a real bird due to obvious reasons. The micro-Doppler signature of an RC bird is shown here, which is clearly much different than the blade's micro-Doppler signature we got from the drones, from the fan's blade experiment. And when we perform this experiment with real birds, many times we can generate enough data, which we can feed into a classification algorithm that can tell us whether the target is a drone or a bird.
Drone and bird classification. This project aims to classify the image input as either a drone or a bird. The image input which we give to the system will be analyzed and predict the results, and the predicted result will be given as output. Machine learning algorithm, convolutional neural network, is used to classify the image. CNN is used for image classification and recognition because of its high accuracy, and it can automatically detect the important features without any human supervision. The main building block of CNN is the convolutional layer. Convolution is a mathematical operation to merge two sets of information. In our case, the convolution is applied on the input data using a convolution filter to produce a feature map. After a convolution operation, we usually perform pooling to reduce the dimensionality. This enables us to reduce the number of parameters, which shorten the training time. Pooling layer downsample each feature map independently, reducing the height and width, keep the depth intact. The type of pooling that we use in our project is max pooling, which just takes the max value in the pooling window. Here is the result of max pooling using a 2x2 windows. Flatten is the function that converts the pool feature map to a single column that is passed to the fully connected layer. The dataset contains a lot of images of drone and bird. Our aim is to make the model learn the distinction features between the drone and the bird. Once the model is trained, it will be able to classify the input image as either a drone or a bird. The project is entirely implemented using Python. The conceptual framework involved is mainly Anaconda prompt, and we use Keras to implement the CNN. Also, we use a TensorFlow as the back end of Keras. And also we use the package, the OpenCV package, to handle image operation like reading the image, resizing, or reshaping the image. NumPy package also is used to store in NumPy array the image that is read. This is the results of our model that we trained. We set the epoch to 10 in order to train our model 10 times of each full cycle. we have an accuracy equal to 100%, and the loss is 1.16%. So this is the accuracy and the loss graph of trained model. And we can see that the more we train our model, the better we get the percentage of accuracy. And also the more we train our model, so the loss percentage decreases. So this is the summary of our model. Each row represents a layer. Each layer's output becomes the input of the next layer. The parameter columns shows us the number of the parameters that are trained for each layer. The total number of parameters is shown as at the end, which is equal to the number of trainable and non trainable parameters. In this model, all the layers are trainable. So to test our model, so we generate an image without saying if it's a drone or a bird. So when we load the image and we run our program, so we get first the image of the image that we load, and also the program display the prediction results. And we can see to the left side the prediction value of the bird, and to the right side the prediction value of the drone. And we have for this case, the value of the drone is much greater than the value of the bird, which means that the image that we test is a drone. And also our program is able to display the result. In this case, we see it display drone as the result. We use a Doppler radar to collect data of drone and bird. And then we perform signal analysis to obtain the micro-Doppler signature of each. For the simulation, we vary the initial parameters such as rotational speed and wing tip length to obtain many different Doppler signatures, which can be used to train our model. We use a convolutional neural network that can accurately predict whether the target of interest is a drone or not. Thank you for attending the presentation.
Thank you very much, team. Does anyone from the audience have any questions for the team?
Could you go back to the slides with the programming on it?
This one?
Yeah, because okay, there we go. I was just curious to see, because this looks really short, as you know, I would expect it to be kind of really long. So I was wondering if you could summarize basically what went into making this as short as it is, because it looks like it's using a lot of things that probably took a long time to develop.
Yeah, we were thinking to show the all code, to see all the results, but because we don't have enough time, I just took the screenshots, to show the results of the image that we tested.
Okay, and then I did have a question about the one of your earlier slides with like all of the moving things have a different radar. I had a question on those graphs. It was right after the Doppler effect, or maybe before.
This one?
Yeah, the slide right after. I was just looking to get an understanding of how these images looks, because it kind of looks like, okay, the bird is like floating and then it flaps its wings. So I was wondering if that is kind of accurate, because the drone is consistent, but it kind of moves up and down.
Yeah, so that's one of the biggest issues, is that it's hard to classify a bird because it's a very random, it does random things. Like sometimes it glides and then sometimes it flaps its wings. but for a drone, it's much easier. Hence, we have like a sinusoidal pattern, which we can identify the drone from a bird. And on the right side, we have a micro-Doppler signature of a rocket, which is also a sinusoidal pattern due to the because the rocket is rotating consistently. So that's
Okay, that actually makes perfect sense. Thank you.
no problem.
So what was the goal of this project? Was it to just detect drones or just distinguish between drones and birds?
It's to distinguish between drones and birds, because if we just use a regular radar, a radar can see a target, but it cannot tell us whether it's a drone or a bird. It can just tell us, like, if it's a Doppler radar, it can tell us how fast the target is moving by estimating its velocity from the Doppler equation, but it cannot tell us unique information such as whether this is a drone or a bird. The biggest issue we have, that surrounds this project is that the drone and a bird has a similar radar cross-section, which makes it hard for a regular radar to distinguish them. So we need another method that we can use to distinguish whether it's a drone or a bird. If you have a radar, a Doppler radar, and it sees a bird, it might tell you this is a drone, or vice versa. But with this method, we can clearly tell which is which.
Okay. I'm just trying to figure out, like, I didn't get, so I when you talked about the problem, it sounded like it was all about drones, and then you're saying birds are the only failed detections that you could get for drones?
In a way, because
Okay.
like say you have a helicopter, you can clearly distinguish a helicopter from a drone, because the helicopter is going to have a much stronger reflection, because it has a bigger blade, and it's a stronger reflection. But with a bird, we cannot tell if it's a drone or a bird. So we need a way to distinguish them. The goal is to detect drones. That's the ultimate goal.
Gotcha. No, I'm with you. That sounds good. Thank you. The other question I had was, did you validate or verify your models for what was it, the bird motion and the I guess drone stand speed?
Yes. If Tyra, can you go back to the slide with the micro-Doppler signatures? Next. Yeah, right here. So no, go back. Yep. So this is a drone. On the right, we have a two-blade rotor, and as you can see that there are two different waves, two different cosines, and that tell us that this is a two-blade drone. And the period T sub C is the 1 over that tells us the speed, the rotational rate of the blade, which we confirmed because we actually set that parameter. So if we calculate here the speed, we can verify it. And then the tip velocity here is half of the magnitude, which we can, if we obtain the Doppler frequency here, so you can see it's 5,000, and then we can use that number to calculate the tip velocity. We can also calculate the blade length, but we cannot calculate blade length and tip velocity independently. We need one to calculate the other. So if we know the blade length, we can calculate tip velocity and vice versa.
Cool.
Okay, I have one more question. It might be a little bit silly. So as far as distinguishing between a bird and a drone, with the problem statement, it's like something is running into a person, and I feel like regardless of what it is, that's going to be a problem. So I was wondering if like what the point of detecting a drone in particular is, like, can you then control or deflect the drone or something like that?
Our goal for this project was the detection. We didn't focus on what happens beyond that. That's something completely different. But in order for us to take action, if, for example, if you have a terrorist that's trying to commit a crime, they can load a drone with explosion and fly it somewhere and then cause damage. Our goal here is to detect a drone and be able to classify drones. What happens beyond that is a different subject that we did not go into in this project.
Oh, okay, I see. So if you could distinguish something in the air as a drone, it might mean other things versus like if it's just a bird, it's just a bird.
Correct. Yes.
Okay.
Alrighty. I don't have any more questions unless someone else from the audience has more questions for the team.
Are you guys going to be giving this research to anyone?
Maybe. I mean, Dr. Zhang is gonna probably he's doing research on this subject, so he's probably going to be doing further research. So.
Alrighty. Okay, team. Well, thank you very much. And thanks for the presentation. We'll talk to you all later.
Thank you.
All right, thank you.
Okay, yeah, everyone. I think that's a great job and a good presentation.
Thank you.
Thank you, Doctor.
Okay.
It was nice working with you.
Yeah, enjoyed every
And
moment.
thanks so much for your help.
Yeah,
That's anyway, the presentation is perfect. Yeah, thank you.
thank you.
Thank you. Take care.